Alright, welcome back. Let us finish up these slides on number theory and encryption and actually get into the encryption part. There is only one lecture this week because of the midterm, so here is the one and only one for this week. So we ended last time trying to do cool stuff with the Euclidean algorithm. We talked about the extended Euclidean algorithm, and it gave us some numbers that let us express the greatest common divisor of two numbers in terms of those original two numbers, as a linear combination of them. And I promise this is going to be useful when we get to RSA encryption. Okay, we just had to learn it first. The stepping stone to get to encryption is called multiplicative inverses. So let's see how, using the extended Euclidean algorithm, can find us a multiplicative inverse mod n of a number. Okay? So it's a long word, I know, but it's going to make sense once I explain it to you. Okay? So just a normal inverse of a number is, like, you take the reciprocal, right? So the inverse of 4, right, is 1/4, because when you multiply those together, right, 4 and its inverse, you get 1. That's essentially what an inverse means. It's something that you can multiply by to, like, cancel out the original number and make 1. Okay? So we can find inverses mod n of a number. So in weird modulo land, you multiply by two big weird looking numbers and you end up with 1 at the end. Okay, so it's not very intuitive, but it makes sense and it will work. Okay, we can find a multiplicative inverse mod n of a number. Okay, so we have an integer x that we want to find a multiplicative inverse mod n of, and that inverse is going to never be 0, right? Because you can't make 1 out of 0. It's going to be one of these, because those are your other options, mod n. And when you multiply by that inverse that we're calling s, and you take mod n, you end up with 1. Okay? So that's my long overview of this first bullet. Let's talk about how to do it now. Okay, so we can use the extended Euclidean algorithm to find a multiplicative inverse. So the first step you need is, here's your mod, right? You're modding by n. You take the number that you want to find the inverse of, mod n, and you give that and n to the GCD algorithm. Okay? It needs to be 1 for this to ever work, otherwise an inverse does not exist. So you got to make sure that this happens first. You need to get 1 out of the deal. All right? Because once you end up with that, once you find a 1 there, you can find s and t, right? You are then capable of finding s and t such that sx plus tn equals 1. That's the last thing that we talked about last time, right? We can use the extended Euclidean algorithm to find those coefficients. A linear combination of these two numbers making 1. Ooh, nice, nice, nice. And then when you take mod n of everything, because that's what we're trying to do, this goes to 0. You see that? That's beautiful. That's exactly what we want. Because anything that is a multiple of the modulus goes to 0. Like, for example, I don't know, if let's pretend we're doing like 2 plus 42 times 5, right? Mod 5. You remember my explanation of why that's going to go to 0 and give us 2? We can remove any multiple. And so we can do that here too and end up with the equation sx equals 1 in mod n land. So that means we have found our inverse. S, or s mod n, really, if it's a bigger number, is the multiplicative inverse of x. Okay? So that is a very long process to talk about, but it's not too hard to actually go and find the multiplicative inverse of two numbers, right? So let's find the multiplicative inverse of 7 mod 10. So the very first thing we do is the extended Euclidean algorithm to on 7 and 10, right? We try and do the GCD of those. So let me just start us off right where we start with y first, then x, right? And then we take mods. So what's 7 mod 10? Or sorry, 10 mod 7. Well, there's 3 left over. All right, now 7 mod 3. There's 1 left over. And then anything mod 1 is 0. So the answer is 1. Cool. That was our first requirement. Now let's find those coefficients. Okay? So let's express 1 in terms of 7 and 3. So 1 is equal to 7 minus, so it's 2 times 3, right? And then let's express 3 in terms of 10 and 7. 3 is equal to, well, it's just 10 minus 7, right? 1 times 7. It's perfect. And then we can plug that into the equations that we learned about last time. We want to eventually get this all in terms of the original two numbers, so we'll maybe start from the beginning and work our way up. So 1 equals 7 minus 2 times 3. Well, what is, 7 minus 2 times 3. So I have that. And I also know what 3 is, though, so let's replace 3 with 10 minus 7. Woohoo! And that gives me 7 minus 2 times 10 plus another 7, right? So that's, plus 2 times 7. And that makes 3 7s and negative 2 10s. Okay? And so I've just solved for my final equation, haven't I? I've expressed 1 in terms of those original two numbers. So 1 is equal to 3 times 7 minus 2 times 10. And because I want to do mod n for this entire equation, and n, we remember, is 10, the tens part goes away. And so I'm left with 1 is equal to 3 times 7. And that makes the multiplicative inverse, mod 10, of 7, 3. Does that make sense? Because 7 times 3 is 21, mod 10, oh, that's just 1. We can always find it using this process, okay? And this is a very important number to know, to find the multiplicative inverse of another, okay? So definitely yell at me if you have any questions about that. That is definitely a lengthy process, right? But it is working. It's going to give us a very important answer. So I want you to try it now. Find the multiplicative inverse of 35 mod 48. Okay, so some number that you can multiply by 35 and then take mod 48 and end up with 1. Okay? So let's see here. Let's just spell that out. That is, find some number s such that 35 times s mod 48 is equal to 1. Okay? That's what we want to find. So the first thing we do is GCD. Okay? This better end up being 1, otherwise it's impossible. 48 and 35, take the mods. It's 13 is left, right? And then how much is left here? Goes into 26 with 9 left. And then 13 mod 9 is 4. 9 mod 4 is 1. Cool, we ended up with 1 as the answer. So now we build up all our equations so that we can eventually express 48 and 35 and get 1, right? So let's work with 9, 4, and 1. 1 equals 9 minus 2 times 4, right? And then 4 equals just 13 minus 9. And then let's work with these 3. 9 equals 35 minus 2 times 13, right? And then finally, 13 equals just 48 minus 35. It only went in once. All right, so now's the hard part. We have to plug everything in. So let's express 1 in terms of these now. So let's replace the 4 first. All right, so 1 equals 9 minus 2 times, okay, what was 4? It was 13 minus 9. All right, so how many 9s is that? That's, let's see, 1, and then positive 2 more, so that is 3 9s minus 2 13s. All right, and now I know what 9 is. I can replace that in terms of 35 and 13. So let's do that. That's 3 times 35 minus 2 times 13, because that's what 9 is. It's getting us closer, minus the 2 times 13 that I had from before. So how many 35s is that? That's 3 35s. And then how many 13s? It's minus 2, so minus, let's see here. Oh, sorry. Minus 6, and then minus 2 more. So minus 8. Minus 8 13s. Okay, that looks correct. And then, okay, we can replace 13 with 35 and 48, okay? So that's 3 times 35. That's a number that we need and care about. Minus 8 times 13 we want to replace with 48 minus 35. Okay, so finally, how many 35s, how many 48s? So I have 3 over here and -8 over here, so that's negative, positive 8 35s, 9, 10, 11, okay, total. 11 35s. This is what a calculator's for, right? And then we want to subtract 8 48s from that. Okay? So finally, I have something in terms of 35 and 48 that equals 1. Isn't that nice? And once we take mod 48, remember that all of this goes to 0, and that leaves us with 11 times 35, and that makes 11 the final answer. Okay, that's our multiplicative inverse. Okay, so if we spell that out, that is 11 times 35. That's going to give us 1 mod 48. Mod 48, that's equal to, let's just quickly go into Python, because why not? That is 11 times 35. 385. Doesn't look like it'll give you 1 mod 48, but it will. So 385 mod 48. That was the proper inverse in mod 48 land. Okay? So it is a long process, but it gives us a very important number. Okay? That's going to be very helpful for when we talk about encryption. Just a few slides from now. All right, before we get there, I just want to talk briefly about base conversion and number representation, because that's important. I'm sure you've seen this at least a few times already in your computer science classes, but I want to hit it again, okay? Because now you know even more about all this stuff. So let's just talk about our own normal numbers first, and then we'll get into binary and other bases, all right? So we like decimal numbers, okay? We like decimal numbers, and we think it's because we have 10 fingers. So maybe in Simpsons land you would be using base 8 or something. So decimal is called base 10 because it has 10 digits total. Okay? So valid base 10 digits. You have 10 of them, right? They are 0, 1, 2, all the way to 9. Okay, that's 10 total. And I am going to write a bunch of different numbers that look like decimal numbers using a bunch of different bases. So I'm going to use a subscript to say what base I'm in. So if I use base 10, that means, or subscript 10, that means I'm talking about the number 42 in decimal. Okay? So that's how you represent it. Fancy. And so if I was using base 5 numbers, how many digits then am I allowed to use? What are my numbers made up of? Well, you only get 5 digits, right? So it's going to end up being 0, 1, 2, 3, and 4 are the only digits you can use to make base 5 numbers, which is weird to think about, okay? And let me show you how to convert any number in any base back to decimal. And the trick is using an expansion, using the power, using the base as a power, okay? So let's break this number up like we did in elementary school. Into its constituent pieces, like the thousands place, the hundreds place, and then that pattern will follow for the other bases. Okay, so let's break down 1,234 in decimal. You remember from elementary school, it's like, okay, that is 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4. 4 times 1, right? And these are all the places, the hundreds place, the tens place. And once we learned about exponents, we could do it fancier. That's 1 times 10 to the third plus 2 times 10 squared plus 3 times 10 to the 1 plus 4 times 10 to the 0. And notice where the base appears. We're working with decimal numbers, and there's the base. Okay? So you can do the same process, actually, to convert any number in any base back to decimal. Okay? In that direction. So let me show you that. So let's convert 1, 2, 3, 4 base 5, because those are valid digits. It's definitely not going to be the same number, though. Let's convert that to decimal, okay? 1, 2, 3, 4 base 5. That's equal to, well, 4 times, that is 5 to the 0's place, right? Just like it was 10 to the 0 before. Usually you work right to left. Plus 3 times 5 to the 1, right? plus 2 times, that's the 25's place. 2 times 5 squared, right? Plus 1 times 5 cubed. Okie dokie. So that is the main difference. You just, because we're converting base 5, the powers become 5 to something, okay? And apparently 1234 base 5 is 5 cubed plus 2 times 5 squared plus 3 times 5 plus 4. It's apparently 194, really. Okay? Base 10. Okay? So that is the secret. That is number representation, and any base works, right? We know that binary is base 2, so you only have 0 and 1 to work with. Okay? So, yeah, let's talk about bases involving 2. We like, in computer science, we love bases that are powers of 2, right? So we definitely love binary, base 2, but we also like base 8 and base 16 and other things like that, okay? So let's talk about those two. So base 2, called binary, and that means you only have 0 and 1 to work with, yeah? And once you make a binary number, every digit, instead of just like, here's a binary number, instead of saying, this is the binary digit 1, this is the binary digit 1, people shorten that to say, they took a B from binary and the IT from digit, and they called it a bit. Okay, so this is a bit, this is the 1 bit, this is a 0 bit, things like that. All right? So, I guess the first thing that I want to show you is how to convert this to decimal, right? It's the same process. Okay? So that's going to be, well, 1 times 2 to the 0 plus 1 times 2 to the 1 plus, the zeros don't count. That would have been the 2 squared, 2 cubed. 2 to the 4th place, though, has a 1. And so this number in decimal was 16, 17, 18, 19. 19 base 10. Okay? If you have 8 bits, this is like a 5-bit number, right? If you have 8 bits, that makes a byte. And so that's where you end up with megabytes and kilobytes and things like that. But 8 individual bits make a byte. And, well, that's base 2 in a nutshell. You can have other bases, though. All right? Oh, maybe I should say first, here's like the smallest byte, right? 5, 6, 7, 8 zeros. And here's the biggest byte, 8 ones. Try and see what those numbers are. It's good practice. All right? All right, now on to octal. So octal is when you have a number in base 8. You get 0, 1, 2, all the way to 7 to work with, right? And you can make base 8 numbers on using that. If you have never seen the terminal command chmod before, this is where one place in computer science where octal numbers come up. So let's look at the manual page for chmod. Dun, dun, dun. Is there anything that I want to see here? So here is, you can do things with octal numbers to set permissions on files and folders. That's what chmod does. It changes the modification bits of a file. Is there anywhere else that I want to talk about? Let me say that I talked about this. Man chmod. When you have a folder, for example, let's see, where am I? Let's go somewhere that we care about. Windows. Or let's go to my home folder. I don't know. I don't think I have anything here, but let's make a sample file. I don't know, a very silly looking file. There. Empty file. If I do ls-l, here are the permissions for that file. I can, as the owner, read and write it. There's a dash saying that I can't do something. That stands for execution privileges. Doesn't make sense to want to execute a text file, that's why. And then anybody who is in the group that this file belongs to, which is apparently my name also, can only read it. And then everybody else in the world who has who's on this machine can read the file, but they can't write to it. Only me, the owner, can write to it. And so there are 3 bits of information here. There is, can you read, can you write, and can you execute for each permission group, for the user, for the group, for everybody else, okay? And so these three together can be 0, 0, 0, all the way to 1, 1, 1, which is 0 through 7. And you can make an octal number to represent the fact that the modification privileges of this file are right now set to 644, if you want to look that up, where if it's a character, it's a 1, and if it's a dash, it's a 0. Okay, so this is where octal numbers come up. Definitely look into chmod more. I'd be happy to explain it more, but that's all I want to do right now. Because I want to get to hexadecimal, which is even more important than octal. Okay, the hexadecimal is base 16, which means you have 16 digits to work with before you get to the end, right? Which is weird to think about because in decimal we only have 10. We need more now, so we need 16 digits before we need a new place. Crazy. And so we have to introduce letters now. So the number, or the letter 10 in a hexadecimal number means 10 in decimal as a single digit. B means 11 as a single digit. 12, 13, 14, all the way to F being 15. Crazy, huh? So, for example, let's convert FE to decimal. And you might see hexadecimal numbers written like this, with a 0 and then an X after it. This just specifies that everything after the 0x is meant to be interpreted as a hexadecimal number, because like in the terminal you can't write a subscript very easily. Okay, so that's all that means. You might see it written this way as well, but let's convert this to decimal. What does this mean? What number is FE really? So it's E times, it's base 16, right? 16 to the 0, plus F times 16 to the 1. Okay, that's easy enough. But what are these really? That was 15. F was 15 times 16 to the 1, and E was 14 times 16 to the 0, which is just 1. Okay, so 14 times 1. And, okay, what is that? 15 times 16 plus 1, 200, and, oh, sorry, plus 14, 254. Base 10. Isn't that cool? And most languages respect that notation, so this will immediately convert it as well. So it's 254. All right, so you can write big numbers that might take multiple, like 3 digits in decimal, with fewer, because this is a larger base. Okay, so that is hexadecimal in a nutshell. And I talked about how to convert from any base to decimal, and we saw it work for all of them. Okay, so that's one direction. The other direction is a bit harder, sadly. If you want to convert between bases, if you want to convert like from decimal to a base, like from decimal to binary, from decimal to hex, decimal to octal, decimal to base 5 even, sadly the process is more complicated. Okay, so let me show you that. And the trick revolves around extracting digits from a number under a certain base. So let's extract the decimal digits of the number 1,234. Okay, let's do that. So think about what is the operation that you would use, like if you were writing a C++ program, what would be the operation that you would use to take this number and extract the last digit, extract the 4, okay? And it should work for any number, no matter what it is. How do I get the 4 out? So I want to do something like this. 1,234, some question mark process ends me up at a 4, okay? And the answer is mod 10. If I take mod by 10 of 1,234, I end up with a 4, okay? That gets me the last digit, and then we can get all the digits if we're able to like shift away that 4, and so that we're left with 123. We can repeat this process of extract the last digit, make it slightly smaller, okay? So, in that case, how do I take this number and get all but the last digit of 1,234? What do I do here to end up with 123? Okay. And if you think about it long enough, it's kind of like the opposite of mod. It's actually divide. Integer divide by 10, right? Int division. That'll give you 123 because it drops any decimal places. So that shifts away the 4, and now I can do the same process to get the rightmost digit here. That'll give me the 3. Then I can shift that away, get the 2, then get the 1. Okay? That's the process to extract the decimal digits of a number, and it actually works regardless of the base. So this is 1,234 integer divided by 10. That gets me 123. Okay? So we can generalize this idea to convert to any base. Okay? Let me show you it in full, though. This process repeated. Okay? This entire process repeated. Let's extract all the digits from 1,234. So the first thing I do is get the rightmost digit, mod 10. That is 4. Then I will shift away that 4, leaving me with 123. Integer division. And now I work with this number. Now I get its rightmost digit. Mod 10 gets me the 3. And then I shift away the 3 and get me 12. Okay? 1, 2, 3, integer divided by 10. That is just 12. And now I can work with 12, get its rightmost digit. Okay, see the game that we're playing here? 12 mod 10, that's 2. 12 integer divided by 10, that's 1. Cool. If I can just convert, if I can just extract all the digits of 1, I'll be done. 1 mod 10 is, of course, 1, goes in 0 times. And then when integer divided by 10 is 0, and that's actually when we're done. We know that this process finishes once we reach 0. We don't include that in our answer. Okay? And every time you took a modulus operation, you ended up with a digit of the number that you were extracting the digits of. So, and you got them in reverse order. So the number was 1, 2, 3, 4 in that order. Okay? And notice the key. Look at what we're modding and integer dividing by every time. What is that? That is the base. So we can generalize this process to convert from a decimal number to any base. You just take the modulus and integer divide by the base you're trying to convert to. Okay? So let me show you that working. Let's convert 55, base 10, decimal number 55, to base 7. Okay, so we only have like zeros and sixes to work with. So let's do that. All right? Let's extract all the base 7 digits out of 55, and it's going to work doing the same process. Let's extract the rightmost base 7 digit of 55. I'm going to do mod 7, okay? And I don't know how to do mod 7 in my head, so there. Apparently it's 6. Then let's extract, let's shift away that 6 out of the number 55, the base 7 digit 6. So I'll do integer divide by 7. In Python, that's 2 slashes. That's 7, apparently. And then, okay, what is 7? Mod 7. That is 0. Interesting, there's a 0 in that digit place. Let's shift away that 0 out of the number 7, okay? 7 integer divide by 7, that's 1. All right, let's convert that to base 7. 1 mod 7 equals 1. 1 integer divide by 7. Let's get rid of that 1. So we can convert the rest. Oh, that's 0. That means we're done. Okay? So every time we took a modulus by the base we're trying to convert to, here, here, and here, I got a digit. 106. And apparently, the answer is 106. Base 5. Let me show this to you. Or sorry, base 7. That is 6 times 1, right? 7 to the 0, plus 0 times 7, plus 1 times 7 squared. Okay? So that's 49 plus 6. Yeah, that's totally 55. Cool. Hopefully that makes sense. Please yell at me if it does not. But that is base conversion in a nutshell. So now you can convert between arbitrary bases. So like if you want to convert from like 55 base 8 to, I don't know, something base 7, convert from base 8 to base 7. The trick is, okay, just always go to decimal first, because this process only works in decimal, okay? Get it to base 10, and you already know how to do that. That was the previous slide, okay? So always start this process with the number in decimal, because you only know how to do decimal arithmetic, okay? So, yeah, now you can convert between arbitrary bases, potentially having to go between them using decimal. Okay? So that's how you convert between any base that you want. Hopefully that makes enough sense. And there's actually a trick if you want to convert between bases that are powers of 2. Of course, you can always do this longer process, but sometimes you don't have to. Let me show that to you. There is a trick when you are trying to convert in this way between bases that are powers of 2, like binary to hex, hex to binary, hex to octal, all this different stuff. And the reason is that binary is a base that's a power of 2, hexadecimal is a base that's a power of 2, and the trick is actually really simple, okay? The trick is just read off all the digits and you have converted the number, okay? Read the digits like off of this table. That's how you convert between hex and binary, for example. And let me show you why this works. So it's great news though. So here's the reason why you're allowed to read off the digits to convert like hexadecimal to binary or binary to hex. You think of it this way. So the first key idea is if you add 0 to the end of a binary number, you're multiplying that number by 2, right? Just like adding a 0 to the end of a decimal number, that's just multiplying by 10, right? So it's always add a 0 in that base, you're multiplying by that base. Okay, first key idea. Second key idea is, okay, now let's think of this in terms of hex and binary together. If I add a single 0 in hexadecimal, that means I'm adding 4 zeros in the binary equivalent of that number, right? Because a hexadecimal number is multiplying by 16 every time I add a 0. That's 2 times 4, right? So that's really 4 binary zeros. I hope that makes enough sense. So that is the key. That's what's happening there, okay? That means every hexadecimal digit corresponds to exactly 4 bits. If you want to convert a single hex digit, just change it to 4 bits, potentially adding some leading zeros. Okay? That's what you do. So for example, if I want to convert DE to binary, I can just read off the answer. It's legitimately going to be, okay, convert D, that is 1101. Convert E, that's 1110. That is the answer. They're always grouped like that, groups of 4 digits. And the reason this works is because DE is D0 plus E, right? It's leave some room there, add a 0 in hexland, that's D times 16. So that's this with 4 zeros at the end, plus whatever E is, and that's just, okay, we left 4 zeros to be replaced with whatever E was. So definitely try that out. That is really the trick, all right? Same with the other direction. If you want to convert this fancy decimal number to hexadecimal, you just group this, starting from the right, into groups of 4 bits, because every 4 bits is a hex digit. There's secretly a 0 here then. And think about it this way. Okay, yeah, it's this number, that rightmost number, plus this one with 4 zeros at the end, right? Plus this one with 8 zeros at the end. And so that is just, this is, what's it supposed to be? 0, 1, 1, 1. That's 7, right? 7, 0, 0, base 16, plus 0, 1, 0, 0. That's 4. Wait a second. Let's confirm that. 0, 1, 0, 0. Yeah, that's 4. 4, 0, base 16, plus 1, 0, 1, 0. That's apparently A. Okay, base 16. Which is just 7, 4A. You just read them off. Isn't that cute? Base 16. That's how it works. So, yeah, you can really just read off these things. Just group them into the corresponding chunks of bits, and it all works out. That's how you convert between bases that are powers of 2, because of this trick. Okay? Hopefully that is going to be useful for you later. Okay? So, now it's your turn. Give this all a try, please. So, take this number, the starting number 55, decimal, convert it to binary, convert it to hex, convert it to octal, convert it to base 5. Okay? And think about maybe using this idea to save you some time. Okay? What's the best thing to go to first? Think about it that way. All right, so yeah, assuming you've given that a try, let's maybe convert it to binary first, because why not? And then we can get the rest out of binary. That's one valid way of doing it. So 55 mod 2, that is odd, so it's 1. 55 integer divided by 2, that's I have no clue. 55 to 27. Okay, 27 mod 2 equals, it's odd again, so 1. 27 integer divided by 2, not 12, is equal to 13? Yeah, it's 13. Checking my notes. All right, then 13 mod 2, it's just this repeated process. Again, it's odd. 1, 13 integer divided by 2, that's 6. 6 mod 2. Finally, we have an even number, so a 0. 6 integer divided by 2, that's 3. 3 mod 2, that's 1 because it's odd. And then 3 integer divided by 2, that is 1.5, so 1. And then finally 1 mod 2 equals 1. 1 integer divided by 2 equals 0, and then we're done. Okay, so that was a long process. Maybe you want to do a different base first. But every time we took a mod, we got a new digit. So apparently the number is 1101. It's always backwards, right? 111. And you can check that by converting it back to decimal. 110111 base 2. Okay, so that's the binary number. And then I can read off the hex digits by just grouping it like this. There's that, and there's that. 2 real zeros there, right? So what's 0111? It's 7, apparently. So there's a 7 in the rightmost digit. And then what is 0011? That's just 3. Okay, so in hex, it's 37. Isn't that nice? Very easy to read that off. And then the same works for octal. Just group them into sets of 3 digits. So this is 111, that's again 7. And this is 110, which is 6. So it's 6, 7, base 8. And then for base 5, we're going to have to do the math again, okay? Because that's not a power of 2. So 55 mod 5, that is 0. It's a multiple. 55 integer divided by 5, that is 11. 11 mod 5, that is 1. And then 11 integer divided by 5, that is 2. 2 mod 5 equals 2. And then 2 integer divided by 5 is 0. And so we're done. So the answer is 210, base 5. Okay, so those are the answers. They seem to correspond with my notes, so I don't think I made too many errors. That's how you convert, okay? Definitely practice that. All right, now we're finally ready for cryptography. It took us a while, but I promise it's going to be worth it, because all this stuff is finally going to come together in a really cool way and let us encode messages that nobody else can look at. Okay, so here is what cryptography is all about. We have a sender who wants to send a message to a receiver, right? And we want to send it cryptographically so that nobody else can look at it. Okay, we want to encrypt the message, and that is just the process of garbling it so that nobody other than the receiver, and maybe the sender too, can understand it. Okay, that is the idea of encryption. All right, you start with the unencrypted message. That's the thing you're trying to encrypt. That's called the plain text. Like, you don't want that to get in anybody's hands. And then the encrypted message that nobody else can look at and read is called the ciphertext. That's the encrypted form of the plain text. Okay, so like plain text, weird terms, I know. You give that to an encryption algorithm. That is going to be a box. And that spits out the ciphertext, which is all garbled, that nobody else can look at other than the sender and the receiver. And then it's the receiver's job to decrypt it, right? That's the opposite of encrypt, decrypt. And that gives you the plain text again that can be read and understood. Okay? That's the main idea of cryptography. The receiver, in our case, for the algorithm I'm about to describe to you, the receiver must have a secret key, we say. So the receiver has a key that can unlock this ciphertext and actually get the answer out. Okay? They can get the plain text out of the ciphertext, thereby decrypting that message. Okay? And yes, all these terms are really the technical terms. So secret key is in the literature. Crazy enough. Okay? And if you ever read cryptography textbooks, this is just an aside, but instead of like setting up scenarios involving person A and person B, they just use letters to make names, weirdly enough. So you're going to see a bunch of interactions between people named Alice and Bob in a cryptographic textbook, which is funny to think about. So that's cryptography in a nutshell. Let's talk about a few forms of it. The first form is one way of doing it, and then we're going to get into RSA, which is the really cool, hard to break way that everybody loves. All right. So the first kind of cryptography that I want to talk about is called symmetric key cryptography. Okay. In this kind of cryptography, you have the sender and the receiver as usual. What they use, though, is the same key to both encrypt the message and decrypt the message. So that means usually they need to meet ahead of time, right? You need to exchange that same special fancy number or decryption protocol. They need that same key on both of their ends, okay? To make sure that they agree and that they'll be able to understand each other, okay? So here's an example. Let's pretend we are trying to send a very long message to somebody. All right, a very large binary number, because that's all electronic message is anyway, right? Binary can encode everything. We've just noticed that. So here is one way to do symmetric key cryptography that is in fact unbreakable, as long as you are able to securely exchange the key. All right, it's called a one-time pad. All right, it's just a random message, the same length as the message that you are sending. Okay. It is absolutely uncrackable if this is a really random string of bits. Okay? So what you do is you take your original message and you combine it with this thing called a one-time pad, which is a random string of bits. OTP. Here's your message. And that is going to encrypt it when you bring it together like that. And this is the same length as the original message that you're trying to send. And that allows you to encrypt it properly. It's uncrackable, and here's one way to make it uncrackable, okay? So here's one way to encode the data using that one-time pad, all right? It's called the XOR cipher. So you know the exclusive OR operation now? What you do is you exclusive OR the plain text with the one-time pad, and that becomes your ciphertext. The key thing about XOR is if you XOR by the same number twice, you end up with where you started, which is cool to think about. So here is, for example, let's say this is my message, 101100, okay? And here is the one-time pad that I came up with, 111000. That's my random string of bits, okay? So here's the ciphertext that I send to somebody. I do the XOR operation, all of these. So 010100. Okay, that's my ciphertext now. And then on the other end, the person who also has this one-time pad, the receiver has it too, they're going to take this ciphertext, 010100, they're going to XOR it with the one-time pad all over again, 111000, and look what happens. You end up with 101100. Hey, that's the plain text all over again, and it was encrypted. Okay, so that is one way to do encryption that cannot be beat. Okay, that is symmetric key cryptography. You have to agree ahead of time, though, on that key. There is a way to not have to agree ahead of time on a key, and it's called RSA. It is super famous. It's named after the people who discovered it. This is a combination of all their last names. Oh man, this is still used today. It is the greatest, okay? It's a very famous algorithm, so let me teach it to you. So it was named after these people, and it's a kind of not symmetric key cryptography. It's a kind of public key cryptography, which is really weird to think about. Everybody has what's called a public key, which they share with everyone, and a private key, which they keep to themselves, weirdly enough, okay? So You don't have to worry about having to exchange the same key, because that's hard to do. You can just share a public key with anybody and not have to worry about anybody cracking your private key. Okay? So here's how you do it. Here's Alice and Bob. Boop. And let's say they all have public and private keys, right? Let's say that Alice wants to send Bob a message. What's going to happen is Alice is going to use Bob's public key to encrypt a message, and he will decrypt that message with his private key. Okay? And the reason this is unbreakable is because it comes down to like integer math. It has to do with factoring very large numbers. Okay? And factoring is a very computationally hard problem. It's if you've heard that whole p equals np question, this is a very hard problem to do. Okay? It's in that category. So factoring is very hard to do, and this will allow us to successfully encrypt a message. So Alice wants to send a message to Bob. So here is the message, the plain text she wants to send. And Bob is going to share, he's going to shout out his public key to anybody who wants to listen. All right, so here's Bob yelling to Alice, here's my public key. And there it is. It's my best drawing of a key. And this is his public key. So Alice is going to use that to sign the message that she wants to send to Bob. She's going to sign it with Bob's public key. And then she's going to give that to him, that signed message. And that's going to garble it up enough to not be able to be understood by anybody else, even though everybody's allowed to see this public key, first of all. It's weird. And then Bob is over here saving his private key just for himself. And that is priv for private key. That will allow him to unlock this message and get the plain text out. Okay? And so that's a long process, and you're allowed to share a public key with everybody. How does this work? Here it is. All right? Here is RSA. Here's how you generate a public key and a private key. So what Bob does is he selects two very large prime numbers. This will allow it to be very, very hard to factor. P and Q. So those are my prime numbers. Then Bob does this. He calculates the number n, their multiple, and a number phi, their multiple after subtracting 1, okay, those special numbers. Then Bob finds an integer such that this is true. E and phi GCD together is 1, because that will allow you to find a multiplicative inverse of those numbers. Hey, hey. So you just try a bunch of possible e's until you find one that works for phi. And then you can go and calculate the multiplicative inverse. That's why we learned all this stuff. Oh, man. That will give you this number, right? You'll find a d such that multiplying that by e mod phi gives you 1. Cool. And now you have a public key and a private key. So the public key is this pair, n and e. You give that to somebody. That's your public key, those two numbers. And then the private key you save for yourself is the d that you found, that multiplicative inverse. If you do all this, and messages are just numbers, right? If you do all this, the ciphertext to encrypt something is you take your message, your plain text message, you raise it to the power of e that you calculated, mod n, that's the ciphertext. Uncrackable. Unless you have very, very powerful computers and you have like thousands of years of time. So then you can decrypt using the d, your private key, okay? So you compute the same message out, it's the inverse, right? C to the power of d mod n, that gives you the original message again. Okay? That's the encryption and decryption process. It's a very long one, but once you do it, you have very powerful encryption. Okay? That doesn't involve having to meet together and share a key first. Okay? You just use your public key. So here, let's do a baby version of it with small primes. Okay? So we're going to do this crushed ice together. Okay? Because it's a long process. We're going to do it together. So what we do first is calculate our n and phi, right, based on p and q. So n is p times q. Let's do that. That is going to be 23 times 29. N equals pq, which is 667. Cool. And then phi is going to be p minus 1 times q minus 1, right? So let's go and calculate that. which is 22 times, let's just do it this way, 22 times 28, that's 616. And now, I have found an E for you already. You just have to search through a bunch of them. But let's pretend that you found a good one. E is 13. Let's use Euclid's algorithm to verify that E and phi are relatively prime to one another, because that's what we need, right? We need to find an E such that this is true. We'll use GCD to make that happen. And then we need to find a multiplicative inverse of E mod 5. E mod 5, excuse me. So let's do that work on the next slide. I've given myself a blank slide to work on. So we'll do that there. We need to calculate GCD of E and phi. And that will give our multiplicative inverse D. Okay? Are you ready? So E is 13, phi is 616. So we're going to do the extended Euclidean algorithm on those numbers. So 616 and 13. So let's mod them. 5, apparently. Okay, cool. 13 mod 5, that is 3, right? 5 mod 3, that's 2. 3 mod 2, hey, that's 1, cool. Check. That is a multiplicative, that is capable of being a multiplicative inverse now. We can find one for 616 and 13, because we got 1 out of the deal. So now let's do our process, our extended Euclidean algorithm, to end up with a number with 1 involving 616 and 13. Okay? So what involving 3 and 2 makes 1? 3 minus 2. What involving 5 and 3 makes 2? 2 equals 5 minus 3. What involving 13 and 5 makes 3? 3 equals 13 minus 2 times 5. And then what involving 616 and 13 makes 5. That's going to be 5 equals 616 minus a lot, right? 47 times 13. Okay? That's going to do it. So that makes 5. And now we can use these to solve for our multiplicative inverse. Okay? So start with this one and just plug everybody in. Okay? Plug the 2 into that equation. That's where we start. So 1 equals 3 minus 2. That is, that 2 is, though, 5 minus 3. Okay? Which is how many 3's? 2 3's and minus 1 5. Okay? And then I can replace the 2, because 2 is 5 minus 3. Let's see here. Oh, no, I'm sorry. That's not what I wanted to do next. I got that, and then I want to replace the 3 next with 13 and 5. I already have 3 and 5. Okay, so 2 times, what is 3? But 13 minus 2 times 5. So that's that, minus 5 now. So now I have it in terms of 13 and 5, or at least I'm about to. That is how many 13s? It's 2 13s. Minus how many 5s? Minus 4 5s, minus 5 5s. Okay. And then, okay, I'm almost there. I need this in terms of 616 and 13. So let's replace the 5 using this. Okay. That's 2 times 13 minus 5 times 616 minus 47 times 13. Okay, that's a big number. Which is apparently, how many 13s? It's going to be 2 plus 5 times 47. 237 13s. Minus how many 5s? 616 is 5 of them. 5 times 616. And now we did it, okay? Because we're calculating the inverse of E mod phi. Phi is 616, which makes this bit go away. Whee, that goes to 0. And so it looks like the multiplicative inverse of 13 is 237, okay? Mod 616. So D, that inverse, is 237, apparently. And that was the hard work. Now we can watch this all play out. All right? So let's pretend that we want to send the secret message, which is the number 515. Let's encrypt that. All right? So we'll calculate the ciphertext, which is m to the e mod n. So C equals m to the e mod n. That is 515 to the power of 13, which was our e, mod n, which is 667 up here. Okay? So that's a big process you got to do. To the power of 13. That's a big, long number. All right? And then I have to do mod 667. And that's 265. That's our ciphertext. Isn't that cool? So this is an uncrackable version of our message that can only be decrypted using the private key. Okay? So now let's decrypt our message to get it back. It's going to be the message, the original message should be, take our ciphertext to the power of d mod n equals, well, that's 265 to the power of 237. Crazy. And then take mod 667. So this is that's even more computation. 265 to the power of 237. That's a large number. But mod 667, what do you know? We get 515 again. And this is how you encrypt and decrypt things using RSA. This is how it works. And now you're finally capable of finishing your homework and your lab. Okay? So it's a long, cool process that kind of explains why we learned about all this stuff, because it is unbreakable with large enough primes. Okay? Absolutely computationally infeasible to break this kind of encryption. Okay? It's very, very popular. It's used all over the internet. Every time you see HTTPS anywhere in a website, it's doing RSA secretly to get you that information. All right. So I think that's everything that I wanted to talk about. So yell at me if you have any questions, and good luck on the midterm, and I will see you next week.